Welcome to this concept explainer, brought to you by CBSE ScoreLab of ProfSam.com. That is ProfSam.com. Today we are taking a deep dive into the very core of Unit 3, current electricity. We'll be focusing sharply on electric current, and our mission, as always, is to strip away all the confusion so you not only understand this concept, but, can secure full marks on any exam question related to it. Okay, so let's start with a simple, everyday question. When you flip a switch, the light bulb in your room, it turns on instantly, right?
Yes, of course. It's immediate.
It feels like the electricity is moving at something close to the speed of light.
Exactly. I mean, if there was a delay, we'd probably think something's wrong with the wiring.
This is where it gets really, really interesting. You see that immediate effect. But if we could somehow tag and track a single electron in that wire,
Okay.
we would find it's barely shuffling along. I mean, we're talking about a speed of maybe 1 millimeter per second, sometimes even less.
Wait, what? Millimeters per second? That's slower than a snail. Then how does the light turn on so fast? If the electrons are moving that slowly, that seems impossible. It's totally counterintuitive.
And that disconnect, that paradox between the fast effect and the slow particle motion is the absolute essence of understanding electric current. We need to figure out what current actually is. So let's unpack this. The core idea is that electric current is not the speed of electrons. It's the rate at which charge flows.
The rate.
Yes. It's fundamentally a counting question. We're asking how much charge passes a certain point in the wire every single second. Think of it with an analogy. Let's call it the concert hall analogy. Imagine a huge concert hall is being evacuated. Every person is like a unit of charge, an electron.
Okay, so a huge crowd of people.
A huge crowd. Now the fire alarm goes off. That's like us applying an electric field when we flip the switch. What happens? Everyone starts moving towards the exit door.
Right, they all start moving together.
Exactly. Now, is each person sprinting? No. Each person is walking slowly, shuffling along. That's their individual speed, the drift velocity.
Which is very slow.
Very slow. But because there are thousands of people, or in a wire, billions upon billions of electrons, the flow through the exit door is huge and constant. You see, the current is measuring how many people get out per minute. It's not measuring how fast each person is walking.
Ah, I see. So it's the collective movement that matters, not the individual speed.
Precisely. That continuous, predictable flow is what makes electricity useful. Static electricity is just a sudden spark. It's unpredictable. But current is measurable. It's controllable.
So the individual electrons move slowly, but their coordinated flow is the actual current.
You've got it. Now, let's build a mental image. Picture a copper wire, but magnified a billion times. You'd see a sea of electrons just jiggling around randomly.
Okay.
They're moving at incredible speeds, maybe 1 million meters per second, but in all directions. It's just chaotic thermal motion.
So they're not going anywhere.
Not going anywhere, on average. Now, we connect a battery. This creates an electric field, which is like putting a very gentle slope on the entire wire. Yes. And now, all those jiggling electrons, while they are still bouncing around chaotically, they also start to slowly, very slowly drift downhill.
So the current is that slow downhill drift.
It's the slow, coordinated drift superimposed on top of the fast, chaotic motion. That is the picture you need to have in your mind. Now that we have this mental picture, let's see how NSERT formally defines this. Could you please read the exact definition and formula for current I?
Yes, of course. It says, let delta Q be the net charge flowing across a cross-section of a conductor during the time interval delta T. Then, the current time T across the cross-section of the conductor is defined as the value of the ratio of delta Q to delta T in the limit of delta T tending to 0. And the formula is IT is identical to the limit as delta T approaches 0 of delta Q by delta T.
Thank you. Now, that definition with the limit function can look a bit scary.
It does. Why is that limit part there?
It's there because current isn't always steady. For our exams, we mostly use the simple form I equals Q divided by T. But think about charging your phone. The current is high at the start and then it slowly decreases.
Oh, right.
That limit just lets us calculate the current at any specific instant, even if it's changing. It's just a more precise way of saying rate of flow.
Okay, that makes sense. And the unit is ampere, which is just coulomb per second.
Perfect. So we have the big picture idea, I equals QT. Now we need to connect it to the small picture, the microscopic world of electrons. Hope everything is clear so far. This concept explainer is from ProfSam.com. That is ProfSam.com. So there's a really important formula for your board exams that links the current I to that tiny drift velocity v subscript d.
Yeah.
The relationship is I equals NAVDE. Let's just quickly break that down.
NAVDE. Okay, what's N?
Good question. N is something called the number density. It's the number of free movable electrons packed into 1 cubic meter of the material.
And is that number large?
It's astronomical. For copper, it's about 8.5 times 10 to the power of 28, a massive, massive number. And that N is the secret. That's the solution to our paradox. A is just the area of the wire, and E is the basic charge of 1 electron.
So, because N is so huge.
Exactly. Even though VD, the drift velocity, is tiny, when you multiply it by the enormous number of charge carriers, N, you get a significant measurable current height.
That's the deep dive insight. Current is large, not because electrons are fast, but because there are just so many of them.
That's it. Let's just do a quick calculation to prove it. Imagine a copper wire carrying 1 ampere of current. We know N, we know A, we know E. We just rearrange the formula to find VD.
So VD equals I divided by NAE.
Right, and when you plug in the values, you get a drift velocity of about 0.074 millimeters per second. The math itself proves how slow the drift is.
Wow, okay, that really connects the two ideas.
It does, and understanding this is the gateway from electrostatics, where charges were just sitting still, to the world of circuits. This leads us directly to our next big topic, which is Ohm's law. But before that, let's tackle the silent killers. The 3 big misconceptions that can cost you easy marks.
Okay, I'm ready.
Misconception number 1, speed versus rate. The wrong idea is current is the speed of electrons. Students think this because the word flow sounds like speed.
Right.
But the correct idea, as we've said, is that current I is a rate. It's a count of charge per second. The drift velocity, VD, is the actual very slow speed. There are 2 different things.
So I have to remember, current is how much charge, drift velocity is how fast the charge moves.
Perfect. Misconception 2, the instant effect. The wrong idea. If electrons are so slow, the light should turn on slowly.
This was my exact confusion at the start.
And it's a common one. The correct idea is that you have to distinguish the signal from the particle. The electric field, the signal, propagates at nearly the speed of light. It tells all the electrons in the whole wire to start drifting almost at the same instant.
Okay, anchor point. The signal travels fast. The charge carriers travel slow.
Lock that in. Now, misconception 3 is a big one, charge depletion. The wrong idea is that electrons get used up by the bulb. So the current going out of a bulb must be less than the current going in.
Wait, that actually sounds logical. The bulb uses energy from the current to make light, so shouldn't the current get weaker?
And that's the trap. You're confusing energy with charge. The law of conservation of charge is absolute. Charge is never used up. The electrons deliver energy to the bulb, but the same number of electrons that enter the bulb per second must also leave the bulb per second.
So the flow rate, the current stays the same.
The current is identical at every single point in a simple series circuit. What decreases is the electrical potential energy of the electrons. That energy is converted to light and heat.
Okay, that is a very important distinction. Current is conserved.
Yeah.
Energy is dissipated.
Exactly. Now let's get you some memory anchors so this stuff sticks. For the formula I equals QT, just think I equals Q'd over T. Silly, but it works.
I equals Q'd over T. Okay, got it.
And a phrase to remember the big paradox. Current is huge due to density and not speed, VD.
Density, not speed. I'll remember that.
Finally, that physical gesture. Hold up your hand, wiggle your fingers really fast in one place. That's the fast, chaotic thermal motion.
Okay, wiggle.
Now, while still wiggling, tilt your hand and just slowly creep it forward. That slow creep. That is the drift velocity. The coordinated creep is the current.
I see it now. The fast random motion with the slow overall drift.
That's the one. Okay, to summarize this entire deep dive, here are 3 exam-safe facts you must remember. 1, electric current I is the rate of charge flow. It's I equal to T, measured in amperes. It is a count, not a speed. 2, this macroscopic current comes from the microscopic drift of countless free electrons. The formula that connects them is I equals NAVDE. The current is large because N is large. And 3, remember the convention. By historical habit, we say conventional current flows from positive to negative. This is opposite to the actual flow of electrons, which go from negative to positive. You just have to accept this for solving problems. To get maximum marks in 12 CBSE physics, chemistry, and maths, visit ProfSam.com.
That is ProfSam.
Yes, ProfSam.com. Thank you for joining us for this deep dive. Study hard and all the best.